in this lecture I shall deal with the principles of X-ray diffraction. Let us suppose that we have got a piece of metal as outlined, and we have a strong beam of incident X radiation falling on this piece of matter. Now, the purpose of having the beam of X rays falling on this piece of matter is we want to find out some pertinent information regarding what is there inside with the help of X-ray with the help of the X-rays. Now, we find in most of the cases when a beam of X-rays is incident on a piece of matter, if we find out if there is any X-rays coming out of the matter in any direction, we will score a blank. That means, under most circumstances there will be no X-rays coming out from the material. Only under some special circumstances a part of the incident radiation will come out of the material, carrying with it all the important information regarding the crystallography of the material. Now, this process is known as the process of diffraction. Usually, the beam which gets diffracted is much weaker compared to the intensity of the incident radiation. Approximately 1 or less than 1% of the intensity of the incident beam is obtained as the diffracted beam from the material. So, the diffracted beam is always very weak. Now, inside the piece of material we have a number of atomic planes as shown with a number of atoms lying on each plane. Now, we know that whenever a beam of X-rays is incident on an atom, these X-rays will interact with the electrons in the outer shells of the atoms, and due to this interaction the incident ray will be scattered in all directions. So, in that sense these atoms are nothing but some scattering centers, and X radiation will be scattered in all directions from the scattering centers. Under normal circumstances, these X radiation which is scattered by the atoms, they will interfere destructively with one another, as a result of which there won't be any X-ray intensity coming out of the material, so to say. Only under some special circumstances which we will deal with now, we find that there can be a weak beam of X-rays coming out of the material due to some constructive interference of the scattered radiation, and this is known as the diffracted beam. Now, analyzing the diffracted beam, it is possible to find out lot of information about what is there inside the material, what are the locations of the various atoms, what is the underlying crystal structure, what is the unit cell like, what is the lattice parameters of the material, etc., etc. Now, diffraction, as I said, is possible only when there is a constructive interference between the scattered rays. Let us suppose that we have got a wave propagating in this x direction. Now, this wave has got an electric field attached with it. Now, if the electric field is plane polarized, that means it will be in this particular plane only, this is the variation of the field, from point to point. Now, if we take two wave fronts, one along m dashed and another n dashed, and if we suppose that two individual waves 1 and 2 emanate from this wave front m prime and move along the direction of propagation in the same manner, then what will happen? At this wave front we will have the two waves completely in phase, and therefore, if we add up these two waves, there will be a total constructive interference, and therefore, the amplitude will be very high or the intensity will be very high. Now, if we consider another two waves, say 1 prime and 2 prime, they start from the same point on the same wave front at the same phase, and then one travels say along a straight line, another travels in a curved path and traverses a longer path, then it may so happen that on the wave front n prime, we will have for 1 prime the wave 1 prime will have its crest at this point, and the same point the wave number 2 prime has got its trough. So, you see that if we add up these two waves, the crest and the trough, they will nullify each other, and as a result there won't be any resultant wave coming out, so to say. Let us consider a third case, say two waves 1 prime and 2 prime emanating from the wave front dashed, one travelling in the straight line and in the other case is travelling in a curved path with longer way. Now, if we measure the number of waves, number of wavelengths from this point to this point, that means from the wave front prime to prime, we can see that here 1, 2, 3, 4, 4.5 waves for the wave 1 double prime coming over on the front prime. That means, if we calculate the number of wavelengths from 1 double prime to the wave front at n prime, we can see that there are a number 1, 2, 3, 4, 4.5 or rather 4.25 wavelengths between these 2 points. Similarly, if we calculate the number of wavelengths between 2 double prime and the wave front n prime, we will see that there are 1, 2, 3, 4, 5.25. So, there is a 5.25, and in the above case there is a 4.25. The result is both the waves will show their crest at the wave front n prime. That means, in this case also there will be total constructive interference. Now, in this particular case, the total path difference between 1 double prime and 2 double prime is 1 single wavelength. In case of 1 and 2, the total path difference was 0. In the other case, the total path difference is the same, and you have got the crest of one, the crest of one lying at the trough of another one. Therefore, they nullify each other. But in this particular case, the path difference is such that it is 1 wavelength, which is not true in case of the waves 1 prime and 2 prime. So, it is less than 1 wavelength. So, we see that if there is a path difference of 1 complete wavelength, or maybe 2 or 3 or 4 integer number of complete wavelengths, there is a chance that there will be constructive interference between the waves. So, now let us see a particular situation. Say we have got a large number of atoms on a number of atomic planes in this piece of material. Now, depending on the interplanar distance d between the atomic planes, we find that whenever this kind of situation comes into existence, that 2d sin theta becomes equal to n times lambda. N is an integer 1, 2, 3, 4 etc., and lambda is the wavelength of the incident radiation, and theta is the angle of incidence. Then we have constructive interference between the two waves. Say for example, X-ray wave 1 and 2 are incident on the atoms N and M respectively. We find when this condition is satisfied, there is a constructive interference between the scattered radiation. Now, we can drop two perpendiculars from M over here. So, the MO is perpendicular to N1 and MP is perpendicular to this line. So, what is the path difference between ray 1 and ray 2 after they are scattered by the atoms at M and N? The path difference is ON plus NP. So, the path difference ON plus NP, if we look at that, each one of these is equal to d sin theta, because this is d and this is the angle theta. So, this is d sin theta, this also is d sin theta. So, what is the path difference between rays 1 and 2 after they are scattered by the atoms M and N? It is d sin theta plus d sin theta is equal to 2d sin theta, and we have already seen that if the path difference is a single wavelength or multiple wavelengths, complete wavelengths, then there will be constructive interference and we will have what is known as a diffracted radiation. Now, this particular relationship was given by Bragg and it is known as Bragg's law. So, you see that whenever there is a beam of X-rays incident on a piece of matter, unless and until this condition is satisfied, as we have seen, we will not have any diffraction or constructive interference between the scattered X radiation by the atoms in the matter. Now, sometimes the words diffraction and reflection are used to mean the same thing. A lot of people will describe the process of X-ray diffraction as X-ray reflection. The reason is simple. The method of diffraction is such that it resembles physically the reflection of visible light from a mirror. Say for example, when there is a diffraction from matter, then we find that the angle of incidence becomes the same as the angle of diffraction. Now, similar kind of a situation arises when light gets reflected from a mirror. So, say this is the mirror, say ray 1, when it gets reflected, it goes in the direction 1 prime, making the angle theta 1 on both sides. Say ray 2 falling on the mirror, getting reflected along 2 prime, making the angle theta 2 on both sides, etc., etc. And this is very similar to what happens when X-rays are diffracted. In that case, the angle of incidence theta is the same as the angle of diffraction theta. So, physically they look similar, but one thing we have to realize that this kind of a process for X-rays can happen only when lambda is equal to 2d sin theta. That means Bragg's law is satisfied. But here, so it can, for a particular material with a particular set of atomic planes having a particular d value, this condition has to be fulfilled, that 2d sin theta is n lambda, then and then only diffraction or reflection of X-rays will occur. On the other hand, here it does not matter whatever is the angle of incidence, so in all angles of incidence, for all angles of incidence there will be a reflection. So, although physically the two processes look like quite similar, but there is a fundamental difference between the two processes. Now, let us look into the diffraction process more closely. Say for example, we have got an incident beam which is denoted as the unit vector S0. Unit vector means a vector whose magnitude is 1, okay, and the direction is the same as the given vector. So, this is a unit vector S0 which indicates the direction of incident radiation falling on two atoms, one at P, another at O, and suppose this is the direction of diffracted radiation, and suppose a unit vector S denotes the diffracted vector in both the cases. Now, angle of incidence theta is equal to angle of diffraction theta. We put perpendiculars from this point P on this line Pm and another perpendicular Pn on this line. Say these are the HKL planes in the material. Say these are the HKL planes in the material. Suppose this angle here is alpha and this angle here is beta. Now, we take O as the reference origin and say P is a point whose coordinates are u, v, w. Now, if we extend this line up to the point y, so that the magnitude of OY is unity, and if we extend, if we cut out a length equal to unity on this line and then join this point with this point, then this vector will be the vector S minus S0, because this vector is S, this vector is S0. So, this vector is nothing but S minus S0 vector. Now, the path difference between the two scattered rays in this from the two atoms at P and O will be equal to OM plus ON. So, the path difference delta will be equal to what is OM? It is OP cosine alpha and ON is OP cosine beta. So, we can write it as OP dot minus S0 vector plus OP dot S vector. Now, why it is minus S0? Because we take all measurements from the origin O. So, OM plus ON. So, it gives us OP dot minus S0 vector plus OP dot S vector. So, it will be OP dot S minus S0 vector. So, what will be the phase difference between these two rays? It will be equal to 2 pi by lambda, where lambda is the wavelength of the incident radiation, into the path difference delta. So, for delta we write OP dot S minus S0. So, it is 2 pi S minus S0 by lambda dot OP. Let us take the S minus S0 by lambda vector as the sigma star HKL vector in the reciprocal lattice. So, sigma star HKL vector in the reciprocal lattice is nothing but HS star plus KB star plus LC star vector. So, OP, how much is OP? We know that OP is the line joining the origin to the point UVW. So, we can write OP is equal to UA plus VV plus WC. The ABC are the lattice parameters in the real lattice. So, now the phase difference phi is again can be written as 2 pi S minus S0 by lambda dot OP, that means is equal to 2 pi HS star plus KB star plus LC star dot UA plus VV plus WC, which makes it equal to 2 pi to HU plus KV plus LW. Now, H, K and L individually, these are all integers. Again, U, V, W individually these are all integers. So, the phase difference in case of a diffraction will be an integer multiplied by 2 pi. Again we know that the vector s minus s0, if we take its magnitude, it will be equal to yz plus xz. So, it is equal to oy sin theta plus ox sin theta, but what is ox and oy? Ox and oy are having unit length. So, it is 1 sin theta plus 1 sin theta, which makes it equal to 2 sin theta. So, now we can write s minus s0 by lambda, if this is the vector sigma star HKL in the reciprocal lattice, then the magnitude of this vector is the magnitude of this vector, and we know that magnitude of this vector is nothing but 1 upon d HKL. So, in other words, we can write s minus s0 vector, its magnitude is equal to lambda by d HKL. But again we know that s minus s0 vector, its magnitude is 2 sin theta. So, putting this value here, we can see that we have got the relationship lambda is equal to 2 d HKL sin theta. So, you see that this is the way reciprocal lattice concept can be utilized to derive Bragg's law of diffraction. Now, since the magnitude of s minus s0 is equal to 2 sin theta and lambda is equal to 2 d HKL sin theta, if we make a dot product of A and the vector s minus s0 by lambda, then we can write it A dot, because this vector we took as the sigma star HKL vector. So, it will be A dot H star plus KB star plus LC star. That means, this dot product will give you value of H only. Similarly, if we take dot product between B and s minus s0 by lambda vector, it will be K, and C dot product C and s minus s0 by lambda vector, it will be L. So, what we find that in order that diffraction is possible, these three equations must be satisfied simultaneously. So, these three relationships must be satisfied simultaneously in order that diffraction can take place. Now, these three equations are known as the Laue equations. So, we can say that diffraction will be possible when the Bragg's law is satisfied, or diffraction will be possible if the Laue equations are satisfied simultaneously. The conditions of diffraction can also be shown in a pictorial way by a construction which is known as the Ewald construction. Say for example, we do a construction of this type where we draw a sphere with a radius of 1 by lambda, where lambda is the wavelength of the incident radiation. Say C is the center of this sphere. Now, this sphere is known as an Ewald sphere. So, this vector C to O is having, it is the S 0 by lambda vector, because the incident X radiation is written as the S 0 vector. So, this vector denotes, this is the vector S 0 divided by lambda. Similarly, say for example, if there is a vector at an angle 2 theta, if there is a vector at an angle 2 theta, then that vector will denote the diffraction vector. So, this is the vector which denotes the incident radiation, this vector denote the diffracted radiation. Now, if we join this point to this point, then this must be the vector S minus S 0 by lambda. Say this point is the point H in the reciprocal lattice, that means its coordinates are H K L in the reciprocal lattice, and since it is the H S star plus K B star plus L C star vector in the reciprocal lattice, it will be perpendicular to the H K L planes in the real lattice. So, if this is the vector H star plus K B star plus L C star, because its coordinates are H K L, then we know that this vector will be perpendicular to the H K L planes in the real lattice. So, these are the H K L planes. Now, we know that the magnitude of the vector OH, it is equal to 2 sin theta by lambda. We have seen from previous examples that this vector has got a magnitude which is 2 sin theta by lambda. So, the magnitude of OH, it is equal to the magnitude of sigma star HKL. So, it is 1 by DHKL, because sigma star HKL magnitude of this is 1 by DHKL. Again, magnitude of OH vector is 2 sin theta by lambda. So, equating these two, we can write down 2 times sin theta by lambda is equal to 1 by DHKL, or in other words, lambda is equal to 2 DHKL sin theta, and this is nothing but an expression for Bragg's law of diffraction. Now, this is a pictorial way of representing Bragg's law. Now, it has got a very important connotation. So, in order that Bragg's law can be satisfied, there is an essential condition which is dictated by this drawing. Say for example, if the point H, which is having coordinates HKL in the reciprocal lattice, does not lie on the surface of the Ewald sphere, say if it lies outside the surface or it lies inside the surface, then what will happen? Then all this condition will not be satisfied. So, Bragg's law will not be satisfied. So, in order that Bragg's law is satisfied completely, it is essential that the vector S minus S 0 by lambda must end at a point lying on the surface of the Ewald sphere. This vector must not end at beyond the Ewald sphere or must not end inside the Ewald sphere, but must be exactly on the Ewald sphere. So, this condition is an essential condition for diffraction to take place. Now, as I already mentioned, this sphere is known as the Ewald sphere, and it is also called the sphere of reflection.